All right, so let's talk about 5.7. We're going to come back to this concept of rectilinear motion. I think this is our third time talking about this concept in this course, but each time we talk about it, we're able to hit it from a slightly different angle. Um, and this time when we look at it, we're going to look at it through the lens of integration. So you may recall that the velocity is just the derivative of the position function, and acceleration is just the derivative of velocity, or in other words, the second derivative of the position function. So it follows then that the position function is the integral of the velocity, and the velocity is the integral of the acceleration, right? Now, these indefinite integrals are going to give us a whole family of antiderivatives, and so to find which antiderivative is the correct one, we need some extra information, and we usually call that extra information initial conditions, right? Or something along those lines. But anyway, let me just give you an example. So let's suppose that a particle moves with velocity v of t is cosine of pi t along a coordinate line. Assuming that the particle has coordinate s equals 4, so its position is 4 at time t equals 0, find its position function, right? So it's giving us this initial condition here. Well, let's see. We want to find the position function. We're given the velocity function. Well, the position function should be the integral of the velocity function. And in this case, the velocity function is cosine pi t. So this is going to be the integral of cosine pi t dt. We can do a u substitution here if we need to. You can say let u be pi t. Right, and then du would be pi dt. And so I can put a little pi here, and then I put a 1 over pi out there. So I'm going to have 1 over pi times the integral of cosine u du. And antiderivative for cosine would be sine, right? So this is 1 over pi times sine of u plus c. Or if we want to get in terms of x, then we would say it's 1 over pi sine of pi x plus c. So now, to solve for c, we use this initial condition, right? That s equals 4 when t equals 0. So s of 0, right, equals 4. That's so I'm going to plug in 0 for, for t, not x. So I'm going to plug in 0 for t. I would get 1 over pi sine of pi times 0 plus c. Well, pi times 0 is 0, and sine of 0 is 0. 0 times 1 over pi is 0. And so we just get c equals 4. Right, so therefore, the position function should be 1 over pi sine pi t plus 4. Okay, and that's that. So pretty straightforward. There are a couple of things though that we can talk about here that I think are kind of interesting. So for one thing, we can distinguish between two different concepts that have to do with a particle's position. Regarding a particle's position, should have an apostrophe. Anyway, so two different concepts. The first one is the displacement. The displacement of a particle is its change in position. So it's wherever the particle ended up at the end of the time interval you're looking at, minus wherever it began at the beginning of the time interval that you're looking at, right? So in integral form, we would say this, right? So it would be the integral of the velocity, right? The position is the integral of the velocity, and we're going to evaluate that at time t0 to time t1, okay? So that's going to give us the displacement. That just tells us the overall change in the particle's position. But if we were interested instead in computing the entire distance that the particle traveled, right, regardless of, whether it's moving in the positive or negative direction, then we need to add up kind of the total distance, right? So to do that, we would actually integrate the absolute value of the velocity function. So the distance traveled would be the integral of the absolute value of the velocity function. Okay. So note the similarity between displacement versus distance and net signed area versus total area, right? It's really the same concept. And then also note that displacement is the definite integral of the velocity, while the distance is the definite integral of the speed, right? Remember, the absolute value of velocity is speed. So that's also kind of interesting. Let's practice with this. So suppose that a particle moves on a coordinate line so that its velocity at time t is t squared minus 2t meters per second. Find the displacement of the particle during the time interval from 0 to 3. Okay? So the displacement is just going to be the definite integral of the velocity. So that's not bad, right? It's going to be the integral from 0 to 3 of the velocity. Okay? So that's going to be t cubed over 3 minus 2 times t squared over 2, but that's just going to be t squared, right? And we want to evaluate that from 0 to 3. So plugging in 3, we would get 3 cubed is 27. 27 divided by 3 is 9. So we would get 9 minus 9. Okay, that's kind of interesting. Minus 0 minus 0. Oh, that's really interesting. So we just get 0 minus 0, which is 0. Okay, so the displacement of this thing is 0. In other words, it stops where it starts. Okay, it ends up exactly where it started, I suppose. So that's kind of interesting to note. Now let's find the distance traveled. Okay, because obviously it's not just staying still the whole time. It does have a velocity, right? So it's moving around. The velocity is not 0 over this entire interval, so it's moving. It's just that it ends up at the same place it starts. So its displacement is 0, but its distance should be something else. So find the distance traveled by the particle during that time interval. So we need to integrate from 0 to 3 the absolute value of t squared minus 2t dt. Now in order to do that, the best thing to do is to figure out where t squared minus 2t is positive and where it's negative. That'll tell us where to split the integral, right? We've done this in previous sections. So let's see. T squared minus 2t is going to look like this. So 0, 1, 2, 3. It's going to have, so one place where it's 0 is right at 0, and another place where it's 0 is at 2, right? And being a symmetric thing, its vertex is probably right there. Anyway, in fact, we can go down 1, 2, 3, 4, and that's where it's going to end up. So this is kind of what the graph of the function looks like. So what we want to do is reflect this so that it ends up going up like that. So we're gonna negate this. Right, we're gonna integrate this thing. So I'm gonna say, well, this is the integral from 0 to 3 of just t squared minus 2t dt. And then we're gonna negate, or sorry, not 0 to 3, but 0 to 2. We need to split right at 2, right? So from 0 to 2. And then we need to negate the integral from 2 to 3 of t squared minus 2t, so that we get it to reflect across the x-axis, so that we're always computing a positive integral. Okay, let's see what we get. So we've already done the integration, right? So we know that it's t cubed over 3 minus t squared from 0 to 2, And then we're going to go minus t cubed over 3 minus t squared from 2 to 3. And let's see what we get. So if I plug in 2, I get 8 thirds minus 4 minus, if I plug in 0, I get 0 minus 0. To evaluate this one, if I plug in 3, I get 9 minus 9 minus, if I plug in 2, 8 thirds minus 4. So it's really 8 thirds minus 4, because this is 0, right? So it's really 8 thirds minus 4 plus 8 thirds minus 4. What is 8 thirds minus 4? 4 would be 4 would be 12 thirds. So 8 thirds minus 12 thirds. 8 thirds minus 12 thirds is negative 4 thirds. Now why am I getting something negative there? Why am I getting something negative? This is a little bit odd. Squared. Oh, you know what? It's because I drew the picture wrong. Okay, let me redraw this picture. Look, it's a parabola, but it opens up, doesn't it? It doesn't open down like that. I don't know why I was thinking it would open down. Oh goodness, 1, 2, 3. So 0 and 2, but it actually does this, right? It actually does that. And so it's this portion that we need to flip over, right? So actually what we needed to negate was this. This needed to be negative, and this needed to be positive. Okay, so this is going to be negative, this is going to be positive. Okay, this is making more sense. So, okay, so we've got 8 thirds minus 12 thirds is negative 4 thirds, but then this negative sign makes it a positive 4 thirds. And here we have 8 thirds minus 12 thirds, negative 4 thirds, but this negative makes it a positive. Okay, so we get 8 thirds. There you go. 8 thirds meters. Okay, so 2 2/3 of a meter, I guess, is the total distance that it travels. So there you go, right? So you can see the difference between displacement and distance traveled, right? Total distance traveled. Okay. Let's talk about acceleration, right? So we've talked about position and velocity a lot. Let's talk about acceleration, and in particular, let's talk about constant acceleration. So if the acceleration isn't changing, it's just like a constant value, right? So if a particle moves with a constant acceleration a, and if the position and velocity at time t equals 0 are s0 and v0 respectively, then the position and velocity functions are these two things, and we can prove this, right? So first of all, we'll get the velocity function. So note that the velocity function is the integral of the acceleration function. If the acceleration is just a constant value, then this integral is just going to be a times t plus some constant, which I'm calling c1 here. Now to find the value of c1, we apply the initial condition v of 0 equals v0, right? Because we were told that the velocity at time 0 is v0, right? So velocity at time 0 is v0. So we're going to say v0 equals v of 0. V of 0 is going to be a times 0 plus c1, right? A times 0 plus c1. Well, a times 0 is just 0, right? And so this is just c1. That tells us that c1 is equal to the initial velocity, v0. And that's how we get v of t equals a times t plus v0, just like we thought we should, okay? Now we do the same thing if we want to find the position function. The position function is the integral of the velocity. The velocity we just found was v0 plus at. We integrate that, we should get v0 t plus 1/2 at squared, and then plus another constant. To find this second constant, we apply the other initial condition, right? We say, well, at time t equals 0, the position is s naught, right? So we apply that initial condition to discover that c2 equals the initial position, and that's how we get the acceleration function. So this is true regardless of hold on, I'm missing an a here, at squared. But this is true regardless of what the acceleration is. So so let's practice with this concept, right? As long as the acceleration is constant, I should say. But yeah, as long as the acceleration is constant, then this is going to be the position and velocity functions. Okay, so suppose that an intergalactic spacecraft uses a sail and solar wind to produce a constant acceleration. By the way, this came straight out of your textbook. I didn't make this up. To produce a constant acceleration of 0.032 meters per second squared. Assuming that the spacecraft has a velocity of 10,000 meters per second when the sail is first raised, how far will the spacecraft travel in 1 hour, and what will its velocity be at the end of the hour? Okay, so how far will the spacecraft travel? Well, we know that if it has this constant acceleration, then the position is its initial velocity, its initial position. I'll write it out. Initial position plus initial velocity times t plus 1/2 times the acceleration times t squared, which in this case, the initial position is 0, right? So we'll say at time 0, its position is 0. Its initial velocity, on the other hand, was 10,000 meters per second. And its acceleration is 0.032. Okay, so throwing that into our calculator, we can say 0.016, so this is equal to 0.016 t squared plus 10,000 t. Okay, so that's the position function. We want to know how far the spacecraft will travel in 1 hour. Well, it's undergoing this constant acceleration that's going to push it forward. So it's never going to have a negative. It's never going to come back or move backwards, right? It's always going to move forwards. So, however far it goes in an hour is going to be its position after 1 hour, right? So we really want to find the position after 1 hour. T here, though, is in meters. Sorry, the acceleration was given in meters per second squared. So t here is in seconds, right? T is in seconds. So we can't plug in 1 hour. We have to plug in something in terms of seconds. So how many seconds are in an hour? Well, there are 60 seconds in a minute, and then 60 minutes in an hour. 60 times 60 is 3,600. So this would be S of 3,600. 3,600, right? So this is 0.016 times 3,600 squared plus 10,000 times 3,600. And let's see what we get. Okay, so I'm coming up with 36,207,360 meters. Okay, so there's its position. Not so it makes a pretty good leap, right? Okay. So that answers the first question. That's how far it's going to travel in 1 hour. It says, what will its velocity be at the end of an hour? Yeah, because it doesn't have a constant velocity. It starts off going 10,000 meters per second, but it's being pushed along faster and faster and faster, right? Because it's got this constant acceleration. So what's its velocity? Well, the velocity is initial velocity plus acceleration times time. That's going to be 10,000 plus acceleration times time, 3,600. Let's see. So maybe I'll say, I'll round this, but it's about 10,115 meters per second. Okay. Very good. Here, let's practice a little more with this constant acceleration idea. Oh, so here's an interesting one. Okay, so it says, a bus has stopped to pick up riders, and a woman is running at a constant rate of 5 meters per second to catch it. When she's 11 meters behind the front door, the bus pulls away with a constant acceleration of 1 meter per second. From that point in time, how long will it take for the woman to reach the front door of the bus if she keeps running with a velocity of 5 meters per second? And I suppose kind of a question we'd have to answer before we could answer that one is, you know, is it even possible for her to catch up? It seems like it, right? Because she's 11 meters behind the front door, so you know, she'll cover that distance in about in a little over 2 seconds, because she's running at a pace of 5 meters per second. So a little over 2 seconds she'll cover that distance. However, by the time she gets there, the bus will have moved forward some more, right? So, and the bus is accelerating at 1 meter per second squared. So after 2 seconds, it's going, you know, 2 meters per second, I suppose. I think she can probably catch it. I think she can probably catch it. Well, let's see. Okay. So what I'm going to do is I'm going to say at this instant when she's 11 meters behind the front door of the bus, I'm going to say that that's time 0, and I'm going to say that the bus's position at that time is also 0. Okay, which means that her position at time 0 is -11, I suppose. But she's going to have to travel a certain distance, right? So I'll call it S sub W for the woman, right? The distance that the woman has to travel in a particular amount of time t. That's going to have to be equal to the distance that the bus will travel, which I'll call S sub B, within that same interval time t. But she has to run also the 11 meters that she was behind to begin with, right? So she has to go as far as the bus goes, plus an additional 11 meters to catch up to it. Okay. Very good. Now we know that she runs at a pace of 5 meters per second. So the distance that she's going to travel in t seconds is going to be 5 times t. So 5 times t is equal to the position of the bus after t seconds plus 11 meters. Or in other words, the speed of the bus after t seconds is 5t minus 11. On the other hand, or the position of the bus rather. On the other hand, we know that the bus is pulling away, it says, with a constant acceleration of 1 meter per second. And we have a model for the constant, for the position, right? The position of a particle undergoing, you know, constant acceleration is going to be the initial position plus the initial velocity times time plus 1/2 times the acceleration times time squared. Well, in this case, for the bus, the initial position we said at time 0, we're going to call that initial position 0, so this is 0. At time 0, its velocity is 0, so its initial velocity is also 0, so those things are gone. The acceleration is just 1, right? 1 meter per second squared, so it's 1/2 t squared. that's the position of the bus. So we have two different expressions for the position of the bus. They should be the same thing, so we can set them equal to one another and then solve for t. Okay, so I'm going to say 1/2 t squared equals 5t minus 11. And then to solve that for t, of course, we want to move everything over to one side. Maybe multiply through by 2 to clear that fraction. So I'm going to get t squared minus 10t plus 22 equals 0. And then I wonder if that can be factored. 11 and 2 would get us 22, but that's not going to get us negative 10, is it? So I think you just have to use Pythagorean. I think you just have to use the quadratic formula and say t equals negative b plus or minus the square root of b squared minus 4 times 1 times 22. So 4 times 22, 88 over 2a. Okay. 100 minus 88 is 12, right? So this is 10 plus or minus square root of 12 would be 4 root 3. Or if you prefer, we can reduce by 2 and call this 5 plus or minus 2 root 3. Okay, so she definitely catches the bus. Now why are we getting two solutions? I wonder what these are. So let's plug it in. 5 minus 2 root 3 is about 1.5. And 5 plus 2 root 3 is about 8.5. Is that right? I feel like that can't be right. Oh, I messed up here. This should be a 2. This should be a 2. Square root of 12 is 2 root 3, which means this should be a 1. Okay, so no, that's not right. 5 minus root 3 is about about 3.3. 5 plus root 3. I'm glad that we thought about whether or not she could even catch up to the bus at the beginning, because I kind of thought it was going to take her a little longer than 2 seconds. So the fact that I got 1.5 kind of told me that something went wrong. But okay, there you go. So we're getting two different answers, 3.3 and 6.7. Now, why are we getting two answers? So the reason is because the woman is running at a constant rate, but the bus is accelerating. Okay, so it'll take her 3.3 seconds to catch up to the bus, but then if the bus doesn't see her, let's say, and she keeps running, then she's actually going to run past the bus because she's running faster than the bus at that point. But the bus is accelerating, so eventually the bus will catch back up to her, and it'll take 6.7 seconds for that to happen, for the bus to catch up to her. And then the bus is going to continue accelerating and leave her in the dust after that. But that's why you're getting two different answers. So I guess really the best answer is 3.3, right? It'll take her 3.3 seconds. That's not bad. That's just a short little sprint to catch the bus. Okay, let's look at another one. Now, to answer the next couple of questions, you have to know that the Earth's gravitational pull is about 9.8 meters per second squared, or 32 feet per second squared. Okay, but with that in mind, let's answer number 5. It says Nolan Ryan, a member of the Baseball Hall of Fame and one of the fastest baseball pitchers of all time, that should say baseball, was able to throw a baseball 150 feet per second. That's in miles per hour. That would be over 102 miles per hour, right? So that's really fast. So he was able to throw a baseball 150 feet per second. During his career, he had the opportunity to pitch in the Houston Astrodome, home to the Houston Astros. The Astrodome was an indoor stadium with a ceiling 208 feet high. Could Nolan Ryan have hit the ceiling of the Astrodome if he were capable of giving a baseball an upward velocity of 100 feet per second from a height of 7 feet? So if he can throw a baseball 100 feet per second straight up into the air, right, from an initial height of 7 feet, because, you know, his own height plus the height of his arm, I guess, when he releases the ball, could he hit the top? Could he hit the ceiling of the Astrodome, which is 208 feet high? Well, this is an interesting question. So what's interesting about it is that he's going to throw the ball straight up into the air with an initial velocity of 100 feet per second, but as soon as the ball leaves his hand, gravity is going to start to pull it down at a rate of 32 feet per second squared. In other words, the acceleration is negative, right? The acceleration is negative 32 feet per second squared. So, oh goodness, how would we do this? Well, so I suppose what we'd want to do is see if the position of the baseball could ever be 208 feet. Well, let's get a formula for the position of the baseball. Right? So it's going to be initial position. Let me just write it out. Initial position plus initial velocity times time plus 1/2 times the acceleration times time squared. So in this case, the initial position we said was 7 feet. The initial velocity we're going to say is 100 feet per second. And the acceleration we decided was 32 feet per second squared, but in the negative direction. So actually I'm going to make this a negative. I'm going to make this negative. 1/2 times 32 is 16, so I'm going to say minus 16t squared. So something that occurs to me is, so one way that we could solve this problem is we could say, okay, now let's set this equal to 208 and then solve for t. Of course, you're always going to get solutions to a quadratic equation, but they might be non-real. And so if we get non-real solutions, then that tells us this is impossible. He can't hit the ceiling. If we get real solutions, then that tells us that yes, he can hit the ceiling, and t will tell us when that happens. Or maybe if we get a negative value for t, then it doesn't really make sense either, right? Because that would mean that he hits the ceiling before he lets go of the baseball somehow, which wouldn't be possible. So that would be one way to do it. But another way that occurs to me to do it, now that I'm thinking about it, is we could find the maximum height. We could find the maximum position, which would require us to take derivatives. But if you take the derivative of the position function, what do you get? Well, you just get the velocity function, which tells me I should have just tried to get the velocity function to begin with, right? So let's do that. Velocity function is going to be initial velocity plus acceleration times time. In this case, 100 feet per second minus 32 feet per second squared times time. And we want to know when that velocity is equal to 0. Okay? Because that'll tell us the time at which the ball reaches its maximum height. Okay, so if this equals 0, then t would equal, well, we would add 32 over to the other side and then divide by 32. 100 divided by 32. And that reduces to 25/8, which is 3.125. So the ball reaches its maximum height at 3.125 seconds. Now let's figure out what that height is. So what is that maximum height? Now to find that out, we plug it back into the position function, right? So we're going to say the position at 25/8 of a second is going to be 7 plus 100 times 25/8 minus 16 times 25/8 squared. And let's see what we get. So 7 plus 100 times 25/8 minus 16 times 25/8 squared. That comes out to 653 over 4, which is approximately is exactly equal to 163.25 feet. So that's the maximum height of the ball. Does he hit the top of the Astrodome? No. The ceiling is 208 feet tall. So we say no, right? The answer to the question is no. Nope, he can't hit the ceiling. Another interesting question would be, what would the initial velocity have to be in order for him to be able to hit the ceiling? Right, so you could play around with that a little bit. But anyway, moving on, one more example for this section. So this one says, a penny is released from rest near the top of the Empire State Building at a point that is 1,250 feet above ground. How long does it take for the penny to hit the ground, and what is its speed at the time of impact? Okay, so how long does it take for the penny to hit the ground? Okay, so when the penny hits the ground, it's at a distance of 0 feet from the ground, right? So we want to know when its position is 0. In order to figure that out, first we need to get a formula for the position function. So let's do it. Again, the penny's just being dropped, right? And so the only force it's undergoing is the gravitational pull of the Earth, right? So anyway, so the position function is initial position plus initial velocity times time plus 1/2 times acceleration times time squared. Its initial position is 1,250 feet. Its initial velocity is 0. Right, because it's just being dropped. So at the point that right at the instant that it's released, its velocity is 0. Its acceleration, on the other hand, so again we're working with feet. So the acceleration is negative 32 feet per second squared. 1/2 times that would be negative 16, right? So this is negative 16 t squared. That's its position. We want to know when that equals 0. So we'll say S of t equals 0, right? Implies that negative 16t squared plus 1250 equals 0. Can we factor out a 16? 1250 divided by 16? No. We can only factor out a 2. How lame. Well, that's okay. Actually, we don't even need to do that, do we? Because we can just take square roots. So we'll say okay, so 16t squared equals 1250. That means t is going to be plus or minus square root of 1250 over 16. Now my calculator will do this, we'll do the simplification pretty nicely. So I'm coming up with 25 root 2 over 4. Now obviously it doesn't make sense to say that it's on the ground at negative 25. That would be before the penny was even released. So we're going to take the positive version here. So it takes about 8.8 seconds for the penny to hit the ground. Now the next question is what is its speed at this time? Well, the speed is the absolute value of the velocity. So let's find the velocity and then we'll just make the answer positive, okay? So the velocity is initial velocity plus acceleration times time. In this case, initial velocity again was 0 and the acceleration is negative 32 feet per second squared. So v of we'll plug in 25 root 2 over 4 equals negative 32 times 25 root 2 over 4. Okay, and so that comes out to negative 200 root 2, or in other words, negative 282.8. That's really fast. Okay, so the speed, right, we would say absolute value of v of, 25 root 2 over 4 is approximately 282.8 feet per second. That's fast. That's faster than Nolan Ryan can throw a baseball. Almost 3 times as fast. So that's really fast. It's almost like 300 miles per hour. Anyway, so that's that. That's all I have to say for this section.